In the previous video in this series, I expanded, initialized, and applied boundary profiles describing the rotor 1 wake and the rotor 2 potential flow to the inlet and outlet respectively to the stator 1 row. In this video, I'll set up a Fourier Transformation transient blade row analysis and post-process the results so we can observe the fluid's transient behavior and determine the stator's aerodynamic performance. With my boundary profile set, I'll change my analysis type to transient blade row and set up Fourier transformation interfaces upon which Fourier coefficients will be accumulated. I must also designate Fourier transformation interfaces that will be phase shifted. First transformation will collect information on the flow generated by the rotor in front of the stator. This will be set as a rotational flow boundary disturbance with phase-corrected interfaces located at the exterior of the periodic interface. The sampling interface will be set as the boundary in between the two stator passages. The rotor immediately in front of the stator contains 23 passages in 360 degrees. The second Fourier transformation interface will collect information on the potential flow developed by the rotor located immediately downstream of the stator. This information will use the same interface in signal motion settings. The rotor immediately downstream of the stator contains 27 passages in 360 degrees. Note that CFX automatically sets the passing period to the shortest period of the disturbances listed. Since rotor 2 has the shorter blade passing period, the first transformation interface will adopt the time period settings specified for this interface. For time step specification purposes, I'll use the passing period option and split the period up into 40 time steps. The time period settings are used to establish a value for the time period in which each disturbance of interest cycles an integer number of times. For a Frozen Gust analysis, the passing period is automatically calculated by dividing the signal pitch by the relative velocity between the signal and the domain. I'll set the run duration to 135 passing periods, corresponding to 5 full wheel rotations. Notice that the first transformation interface has adopted the time period settings from the second interface. To capture the rotor's passing influence on the stator, I have inserted 3 monitor points, one near the inlet, another near the outlet, and a third in the center of the stator blade passage. Previously, I defined expressions describing the pressure ratio, flow rate, and efficiency for the stator row. These will be monitored throughout the simulation. I can show you the data collected by the monitor points. This plot shows the pressure change at the inlet of the stator as rotor 1 rotates. As we can see, 23 pulses have been captured over a single full wheel revolution corresponding to 1 complete rotation of rotor 1. The monitor at the center of the passage shows an interesting result. Here, we can see more complex signal structure due to the interaction between the front rotor wake and the back rotor potential field. This result conforms with expectations since each rotor demonstrates a different passing frequency. Finally, the monitor near the outlet also shows complex signal structure, although this was heavily influenced by the rotor 2 blade passing. Data describing the flow rate, pressure ratio, and efficiency has also been captured successfully. This information can be used to determine the aerodynamic performance of the stator 1 row. I have opened the results file in CFD-post for more detailed post-processing. You'll notice that the entire stator geometry has been rendered despite the fact that I only simulated 2 stator passages. Using data instancing, I can recreate the solution for the entire stator row, meaning I can observe the fluid's behavior across the entire stator geometry. I have already inserted a turbo surface of constant span located between the hub and the blade tip. Using this surface, I created a pressure contour plot and a velocity contour plot. I also created pressure contours describing the inlet flow field and the outlet flow field. Using these plots, I generated animations showing the pressure contour and the velocity contour at the turbo surface. This animation shows the pressure contour at the inlet of the stator. Conversely, this animation shows the pressure contour at the outlet. As we can see, CFX has successfully captured the complex transient interactions between the front and back rotor signals on the middle row stator using the Fourier Transformation pitch change model. This concludes this demonstration on how to use the Fourier Transformation transient blade row method to set up a Frozen Gust analysis.